is physics. This is electric, chapter 16, electric charge. And fields. So this will deal with what we call static electricity. As opposed to current electricity, which will be in chapter 18. So this will be probably the first test. We get the current electricity, that'll be the exam 2. All right, so what we have here for chapter 16, we have the concept of electric charge. And what we now know is we have, for any atom, right, you have the nucleus, which is positively charged, and you have the electrons, which orbit somehow in that, are electrons. So we have electrons out here, protons in the center, and the charge, we have E minus, which is minus 1.6 times 10 to the minus 19 coulombs. All right, coulombs is the unit of charge, or we use capital C. For the proton, it's plus 1.6 times 10 to the minus 19 coulombs. So they're equal and opposite charges. So any neutral atom has exactly the same, exactly 0 net charge. Any substance like this book, all right, it's made up of many, many electrons and protons, but they all average out so that the net charge of the object is 0. Because we'll see electricity has a very strong charge to it. It's force to it, I should say. All right? I mean, it's gravity is what pulls things down like that, but it's electric charge that makes this book repel my finger. Right? It's not some sort, and this is mostly made up of empty space, but it's the electric charge that causes it to repel. So that's the first part, right? So we'll be using these numbers quite a bit in this semester. All right, so leave that up for a minute. We'll talk about a little bit about insulators and conductors. All right. Conductors like copper allow current electrons to flow through easily. So they flow through easily. Insulators like wood, plastic, electrons do not flow at all. Basically, they just stay right where they are. So that's how that works. So metals conduct electricity very well. So most metals and so on. And then in between, we have what we call semiconductors. When we get into insulators, when we get into current electricity, we'll talk about these in more detail as far as that. So plastics, what we call conductors, insulators. And we'll be using a couple of programs here with the lab, the FET electricity labs. So you just follow the directions for those on the lab handouts as we go into those. And that's the case there. So, I'm not going to do anything on induced electric charge, section 16.4. But I'm going to, there's a lab that will base that, you'll see that in one of the FET labs, this concept we call induced electric charge, like rubbing a balloon causes charge, either electricity either to be pulled away from it or added to it, so it becomes electrically charged. It'll stick to a wall or such. So that's over there. All right, so I'm going to go into 16.5, and this is what we call Coulombs Law. All right, and Coulombs Law is the fact that if we have positive opposite charges attract, like charges repel. We'll see that. So opposite charges attract each other, and we can have this in a law called Coulombs Law, which is given by K. I'll give that number in a minute. Q1, Q2, over the distance between the center of the two charges. Where K is 9 times 10 to the 9th, and I'm not going to put in the units. Q is in coulombs, and R is the distance between them in meters. So this would be the force Q1, Q2, and the distance between them is R. The force attracted is given by that. Now this is very similar to the law of gravitation. So this is for electricity, for gravity, as a comparison, which we did back in one of the earlier chapters, G, M1, M2 over R squared. It's exactly the same form, but instead of charges, we have two masses. Now gravity is always attracted, always attracted. We have never found anything of gravity repulsion. Here in this case, though, K is 9 times 10 to the 9th. Here, G, the gravitational constant, is 6.67 times 10 to the minus 11th. All right, it's a factor of 20 difference. And what we also have that what it turns out, you think gravity is the overwhelming force, which it is, because everything is attractive, everything pulls. But it turns out that if I leave these up for a minute, and we're going to be only dealing with this, if we have all right. Okay, we have the force of electricity is 10 to the 40th times the force of gravity. 10 to the 40th times. As we'll see some other examples, so the overwhelming force, because gravity is attractive, we always notice it, but electricity does not take much charge to make a very strong electrical force between two objects, as far as that's concerned. So let's do an example here of, let's say we have Oh, a force between two charges. Q1 is, say, 5 microcoulombs, which would be 5 times 10 to the minus 6th. And Q2 is 10 microcoulombs, which would be 10 to the minus 5th coulombs. And say R between them is 10 centimeters, which is 0.1 meters. What would be the force between those two? All right? Now remember, micro is 10 to the minus 6th. So that would be, the force would be 9 times 10 to the 9th times 5 times 10 to the minus 6th times 10 to the minus 5th over 0.1 squared, which would be, let's see, 45 times, let's see, 10 to the minus 11th, 10 to the minus 2nd, over 10 to the minus 2nd. Yep. Because that's going to be that's going to 0.1 squared is 10 to the minus 2nd. This is, so that'll be 45 newtons, which is a pretty strong force. So that would be the actual force of just that type of charge. So very small charge, but in reality, this is actually quite large. If we had that kind of mass, micrograms or micro, at that, you'd have incredibly small force. So this is what we're going to be using here, and we're only going to be dealing with two charges in a line. So we're only going to be dealing with charges in a line separate each other. I'm skipping the section on vectors and charges in different directions as far as that's concerned. So you can look at some of the problems there. So what we have here is, right, if Q1 is positive and Q2 is negative, the force will be attractive. If Q1 is positive and Q2 is positive, then the force will be repulsion, right? So you got to take that into account, what the force is going to be. So we have a charge here, and we're going to figure out which way would this go. It would be pulled to the left. If we had a charge, they're both the same, then this one's fixed, then this one would be pushed to the right. So keep that in mind, because force is actually a vector, right? So keep that in mind. The sign of this would actually be negative. It would actually be repulsive. So it would be repel. So keep that in mind with those kind of examples. All right, so K is 10 to the 9 times 10 to the 9th. These are both in coulombs. All right, so that's the first part of 16.7. All right, we're actually not going to do a whole lot of this chapter, so I'll just go through all of it now. All right, and what we're going to look at next, if you do some review questions, and again, we're going to have some simulations. The lab simulations will probably give you a better idea of how this all works. We'll leave that. We'll move on to the next section I'm going to cover. Is next section we're going to cover are 16.8 electric fields. And in this case, what we're going to do is, what if we have a positive charge here, right? A proton there. Then what an electric field is, these are lines that would indicate where another charge would go. So if I have, say, a proton in the center of it, and I put a positive charge, was to put a positive charge there and keep this one again fixed, where would this one move? Well, it would be repelled, so it would actually move outwards. It would move away from. If it was over here, it would move like that. If it was over here, it would move like that. So what we can do is draw what we call field lines, which indicate the direction positive charge would move. So it would go like this. So and you'd have lines going out indicating that a positive charge placed anywhere here would go straight out. Now if we have a negative charge in the middle, then likewise, what we'd have is a positive charge would be pulled in. So for negative charge, we have exactly the same kind of lines, except in this case, all the lines are, arrows are pointing inwards. Okay? So those are the electric field lines. Well, it seems pretty simple for something like a single charge, but what if you have something a little more complicated? So these are single charge. So let's say we have a dipole. Dipole, like a magnet, we'll get into magnet, a north and south pole. A dipole, meaning a dipole has a plus charge and minus charge. So it has a plus and minus charge. Right, so in that case, we'd have a plus here and a minus here, it's fixed. And the question would be, what would happen if I put, say, a positive charge here, or a positive charge here, or a positive charge here, or a positive charge here? All right? Well, in the middle, the one here, it would go straight across. That's pretty easy. Well, if you have something like here, right, it's going to get repelled from this one, so it's not going to go straight out, but it's also going to be weakly attracted to here. And as it gets farther away, it's going to get more attracted to this one. We have here, this one will go like, it'll be attracted to here, but it's still being repelled here, so it'll do this. This one will do the same path this way. So if we loop these around, we can actually see this is what it would look like. And if you've ever done iron filings with magnets, you get the same sort of thing. All right? Now, if they're both the same size, it's more uniform. I'm not going to get into it, but here's some pictures from the book. You have similar ones. They're going to be like symmetric. If we have they're both the same charge, then they're going to be and we put a positive charge. They're both positive, put a positive charge, you're going to be repelled from both of them. And if Q2 is stronger than Q1, it's going to kind of loop more like that because it will be attracted easier by the higher charge on this side. And then finally, if we have two parallel plates, one is plus, one's minus, so we'll get into this quite a bit, the lines are going to go straight across. So I can summarize that a little bit. So if I have two parallel plates, Q1 and Q2, where this is plus and that's minus, the field lines will go straight across. And that's the case there. So that's and actually, yeah. And then we're going to do one last thing here. So the last part here is electric fields, conductors. All right, so this is a conductor, this ball, aluminum ball, and it's got an insulating shield on this thing. So what we can do here is I'm not going to do it here, but this is a principle you ever seen it, a band, the graph generator. And what it is not, what we have here is there's a motor here at the bottom that uses electricity to bring electrons up to this up to here, and these electrons will collect up here as they, as this belt moves up and down. It'll collect up here, and it'll get more and more and more up here, and all these electrons are going to spread out as much as possible. And what'll happen, so he's developed a static charge here. But these electrons are going to want to go somewhere. And if I get near this thing, you can see this on the lab, so if I put my finger nearby, these electrons are going to go flying from there to me and create a small current in my finger, which gives a big shock. You'll get a big spark from there. You've done that whenever you've, in the winter like today, and walking on the carpeting and then touch, say, metal, you'll get a little shock sometimes. Because you're developing, you're charging yourself slightly, and then you discharge it on there. Good example I wasn't really realizing all the time are helicopters. When they're doing rescue missions, the flying propeller, flying blades creates a large static electricity on the helicopter. So before they pick somebody up, they have to discharge electricity into the groundwater. Otherwise, the person being lifted up would get a big shock, and then that could kill themselves. So this is a concept here of static electricity. So the electricity here stays all the way outside. Now what's inside, interesting, is that, so outside here, this thing, this ring, this ball of charge, the electric field goes straight out from the center, much like a point charge. So it's exactly like a point charge, but it starts from the surface. So I'll put a positive charge there, it would try, or a negative charge, because these are all electrons, will go flying off in that direction. So this is the electric field outside. But what's interesting is inside, the electric field is zero. Inside a conductor, the electric field is zero. There's some good examples of that, of demonstrations of, say, what they call a Faraday cage. Is if I have a cage of wire, and you put somebody inside and get this thing up, so it can be as many as 20 million volts of potential we'll get into voltage, and you get a big spark. It will actually go around this thing, and the person's side will stay perfectly okay. It's the same reason why a car inside a car, assuming it's got a metal frame, which all of them still do. All right. If it gets struck by lightning, the electricity will flow around into the ground. And inside, because it's made out of metal all around, the person inside will be fine. It's the same thing for airplane. Planes made out of metal, if they get struck by lightning, the metal will conduct around, fall off, and go back to the ground. Now, the actual struck by lightning can be very frightening because it does make a big boom, but the plane, based on the way I'm designed today, have no problems. I think the last crash due to lightning was back 1963 or 53. It was a long time ago. Planes on average are struck about once a year. So that's the case there. So anything with metal will divert the electric field around. So the inside, E is 0, outside is just like a charge. So that's section 16.9, and there'll be some links there. And that is basically the end of chapter 16. So that is 16. The final chapter for the first test, chapter 17, we'll get into potential difference in voltage. And that'll be the final chapter 17.